Hello, Houston. We're just sitting here breaking precedent. Last two times we haven't been organized when we started, so today we thought we would be. What I want to do is to drop back and look at the difference threshold concept again. We kind of rushed through that right at the end of the last lecture. Remind you of Weber's law, and then specifically using what is called the method of constant stimuli. When we're trying to measure a difference threshold, we're going to end up producing a set of results that look like this if we use the method of constant stimuli. The example I kind of used in a rush at the end of the program last time was that if we had a 300 gram standard weight and we were interested in how much we would have to add or subtract from that weight in order for you to be able to detect the difference, we would use the method of constant stimuli. What I would do is put up a barrier between me and thee. On your side, I would have a standard jar, maybe say a baby food jar filled with 300 grams of buckshot or BBs that had had black wax poured in on it. So all the jars that you're going to see are going to look the same. And in each case, what you would do is lift the standard, and then I'm going to have an array of jars on my side that range from, say, 285, 288, 291, and so forth up to 315 grams. And I will randomly select from the 11 jars I've got on my side and hand it out to you. And what you're going to do is lift the standard and then lift the comparison jar each time and tell me after lifting the comparison jar whether that's heavier or lighter than the standard. And in each case, all we're going to do is record jar by jar by jar the percentage of time that you label it heavier, the percentage of time that you label it lighter. And so we'll end up with a set of results like this after we have run literally hundreds and hundreds of trials. So you're going to make those comparisons a number of times, and then we summarize the data, and if we're lucky, we end up with a set of data such as you see on the screen there. And the point then is that somewhere along that dimension of jars that range from 285 to 315 grams is going to be a weight that seems to you to be exactly the same. And the way you're going to report that, because all we're allowing you to do is say that second jar is heavier or it's lighter, what you're going to have to do then is kind of split your vote. Half the time you call it heavier, half the time you call it lighter. And that'll show up in our data, which goes progressively, theoretically at least, from very few people ever saying that a 285 gram or a 280 or 270 gram, the lowest weight is heavier, and very often or always saying that our heaviest weight is heavier. So we simply look at the percentage of judgments heavier. That's what's plotted here. Wherever the 50th percentile falls defines what is called the point of subjective equality, okay, or PSE. The point of subjective equality is essentially the aspect of the stimulus package, the comparison stimuli, that seems to you to weigh the same as my standard weight. So that's our point of subjective equality. Another way to think of that is to think of it essentially as the point of total uncertainty. Half the time it feels heavier to you, half the time it feels lighter. So you're totally uncertain and you essentially split your vote. If we go all the way either direction, that is either to lighter or to heavier, you will then always judge the comparison weight as being heavier or lighter. So at some point on each direction out the scales, we reach the point of complete certainty. Halfway between total uncertainty and complete certainty represents what is called a just noticeable difference, or JND. Okay? A JND is a just noticeable difference. In other words, when we start at say, for this subject, suppose they're a perfect subject, at 300 grams, that's the comparison weight that they always judge as half the time it feels heavier, half the time it feels lighter. When they get out to 75% accurate in calling some weight heavier, that distance along the x dimension defines what is called the positive JND, okay? The positive JND. That's how much we have to add to that 300 gram weight in order for it to feel 75% of the time like it's heavier. That is the just noticeable difference. If we go the other direction, if we subtract weight, the other question is, at what point does your judgment drop to 25%? And when we reach that point, that defines the negative JND, or the negative just noticeable difference. So in essence, when we come straight across from the 25% mark, and I'll use the pointer here, though I don't know whether you'll be able to see it on the screen. It's a little bit small, but in essence, when we come straight across from the 25% point to your performance curve, we drop straight down, and this value defines the negative JND. But we've got a dimension here, that is, we've got a distance along the x-axis, the distance between 300 and whatever is this value. is our negative JND. So to determine the difference threshold, and this is where I kind of finished in a rush last time, what you do is to add this distance, the negative JND, to the positive JND, and then divide it in half. So the difference threshold for 300 grams is the average of the negative plus the positive JND. Okay? And that's how we actually measure using the method of constant stimuli. The difference threshold then is simply the positive JND plus the negative JND divided by 2. And that's how you actually calculate a difference threshold. There are several other techniques that can be used, but that is the most straightforward one that we have. Okay? And that basically concludes our discussion of psychophysics. And now what we're going to do, as soon as my blinded eyes can figure out how to get us over to the visual component of this fine course, that's a value judgment, of course, is we'll put that on the screen, and then we'll start talking about the next segment. Hang on just a second here. The computer's fighting with me a little bit. We're going to look now at vision. In essence, when we start talking about vision, we have several immediate kind of statements that we can give to you. We're going to look at a number of general systems here, starting with vision. We're going to look at the physical stimulus and the corresponding psychological attributes. We're going to look at the receptor. We're going to look at how transduction occurs. And by transduction, what I mean is converting energy from one form to another. Okay? When you push on your car and get it moving on a flat surface, you convert your nervous energy into the inertia of that car. You've imparted your energy to that car. You have transduced the neuronal energy and the stored energy within your body into the motion in that car. That is a conversion of energy from one place to another, or one type to another. In our eyes, transduction occurs when light is converted into neural energy. We'll show you where that takes place. We're going to look at functions of the various systems. We'll look at some of the theories regarding how those systems operate, and then finally we're going to look at problems within each of the systems, or with many of them, at least. Now, in terms of vision, it's pretty straightforward. The visual stimulus, no great surprise here, is light. Light is basically a form of radiant electromagnetic energy, but it is only a portion of that energy that we are actually able to see. Okay? We have off one end of that continuum ultraviolet light, and off the other end of that continuum, we have infrared light. We don't see either of those. So we only see the total portion. We convert into a visual experience only a portion of the total electromagnetic spectrum. And so in essence, it stretches all the way from gamma rays to radio waves. We're only going to see a very small portion of it, a very small portion. It's bounded at the lower end by ultraviolet rays, which are shorter, and at the upper end by infrared rays, which are actually longer. Now, the unit of measurement that we use is what's called a nanometer, or an NM, as that's normally talked about. It's also sometimes referred to as a millimicron, or MU, but normally we refer to just a nanometer, which is basically 1/1000th of a meter. In other words, we're dealing with very short waves here. And light waves basically run from 400 nanometers at the violet end of the spectrum up to 700 nanometers, or NM, at the red end of the spectrum. Now, relative to that stimulus, let me burden you with a couple of different features. Well, look at that. I had all those fancy doodah words prepared for you, and I forgot to show them to you. This is an important table. You want to put this on the 3x5 card that is stapled to your navel and be able to flip it up and read it and remember it anytime you want. Let me point out again that the physical characteristics of light are not equal to, they are different from, the psychological attributes that we're going to be talking about today. Okay? So, one of the physical attributes of light, if we were going to put it on an oscilloscope screen, one of the things that we can vary is the wavelength, or the frequency, the cycles per second or nanosecond that a light wave exhibits. And in essence, that's varying the wavelength of the light, as we were just talking about it, ranging between 400 and 700 nanometers. What that alters in our visual experience is our experience of color. The other word that psychologists sometimes use is hue, H-U-E. Hue, or color, is what's altered when the wavelength or frequency of the light wave changes. As that changes, the color that we experience changes. Secondly, another thing that we can vary is the amplitude of the wave. That is, how far it swings off neutral on an oscilloscope. How widely the waves go determines essentially for us the brightness that we experience. So if the amplitude on our oscilloscope is adjusted or very muted so that it's barely cycling, the color that you're going to see is relatively dim. It does not have a great deal of brightness. If on that same scale, however, the amplitude increases from our physical source, then the experience that we get is that the light seems to get brighter. Okay? And the third element is the most confusing of the three, and that is what's called the range or mixture of the light. I'll show you what I mean by this in a little bit, but in essence what it does is to impact the pureness, or what is also referred to sometimes as the saturation level of the light itself. To give you an example of an absolutely pure light, the rainbow colors that you see when sunlight has come down through rainwater on an otherwise absolutely clear day, those colors are representative of very close to purely saturated colors in nature. You can have reds that are redder, you can have reds that are brighter, but you can't have reds that are more saturated than the reds that you see in a rainbow, or the purples, or the greens, and so forth. So those are examples basically of saturated colors. Now, let's look at what is called the color solid. This is a device that's really used only in introductory psychology, but I think it's very helpful in kind of laying out what the dimensions are of the total spectrum of light that we're going to be dealing with, and the various visual characteristics that we have here. The color solid actually represents all three of the dimensions of ways in which the physical characteristics of light can actually change. Okay? We have saturation level is represented by distance from the midpoint. Okay? And you will notice brightness is reflected on the vertical dimension. And the actual color, the hue that you experience, is represented by the position around the circle. Okay? So all three dimensions are represented there, and thus, in theory at least, any color can be represented somewhere within this color solid. So if you have something that's simply on the black, gray, white scale, it's simply going to be somewhere up and down the very middle of this figure. If you have a very highly saturated red of moderate brightness, then what you have is a color that's going to be out on the very left side of the diagram as you're viewing it here. Okay? And then we're going to see that we've got all manner of different colors in between that we can in fact talk about here. So let's isolate the components here and see if we can identify specifically what we're looking at. What I want to do is concentrate specifically on what I'm going to call the color circle. The color circle is basically the middle portion of this diagram, and I'm going to show you some things relative to colors by isolating just the color circle itself. That is, we're going to look at this portion of the diagram, the color circle part. And if we take that circle, we can expand it out. That is, instead of viewing it on a side, we're going to actually flatten it up and look straight down on it. And then when we do that, we can put all of these dimensions on there. That is, if you saw what I did, I simply took that color circle and then rotated it up flat so that we're looking square straight down on it. So we've got maximum saturated color represented here out around the edge. Are you with me in terms of what I've done so far? That's an audience participation question. Yes, okay, we move on. Now, there are several different calculations that we can measure here. One of the things I want to talk about, and I'm kind of getting a little bit ahead of myself here, but in essence, one of the things we can measure here is the additive combination of colors. Let me give you a quick example of what I mean. If I have a pure white stage floor on which I shine a red light and a yellow light, what I will end up with on the stage floor is some shade of orange. That is, the red waves add together to the yellow waves and produce a wave that is somewhere in the orange. I'll talk more about that in a little bit. That's an example of an additive color mixture. But you can't take a can of red paint and pour it into a can and pour in a can of yellow paint on top of it and produce orange, because of the fact that those paints are working subtractively. There is a difference in how we combine colors. One is an additive mixture where you're piling light on top of light, and the other is a subtractive mixture. Maybe another way to think of it is that if I shine a light directly at you that is pure white, and then I drop a red filter in, In essence, what the red filter does is to subtract everything except the red light waves that it allows to go through. Okay? So that's a subtractive mixture of colors. If theoretically I were to have a white beam shining right into your eye and I dropped a red filter in along that path, if I then dropped in a yellow filter, you would see nothing, theoretically. That is, if the filter were absolutely perfect, when you drop in the red, that stops everything but the red light waves, and if you then drop in a yellow filter, what you've done is to stop everything else. And so nothing should go through, theoretically. Now, in fact, as we know, it does happen. That is, some light does get through. So when you go to a theater, a stage production, if you look up at the lights, my 6th grade picture, I'm actually standing on the top row because I was tall at that time at the left end. It was the first time I had ever actually stood on the stage and noticed that in fact they had red, green, blue, and yellow lights up there. And in fact, because they were taking our class picture that day, all of those lights were on. And so I'm standing up there looking, like this, my class picture, I'm this way. And what I'm doing is thinking to myself, now let's see, red, yellow, green, and blue, but when I look down on the stage floor, it's white. And I don't know what I was expecting, maybe polka dots of yellow, red, green, and blue or something. But in fact, of course, what had happened there was that what was being demonstrated was an additive mixture of the colors. When the red, green, yellow, and blue were all on simultaneously, what shows up on the stage floor is white, as we'll show you here in a little bit on the color circle. But in essence, the color circle is limited to additive mixtures of colors. And when we look at this circle, we can actually show you several ways to actually calculate the color that you're going to end up with. So if you watch carefully the lines that I'm going to put on here, what I'm going to do is to start with a red color. So we're going to have a very saturated red color that I'm going to start with on the stage floor. What I'm going to mix with it is a yellow color, represented by the second line here. In order to determine how bright the color will be that we'll end up with, we need to do two things. We first of all have to put a connector between those two lines, okay? So we've got a line that goes straight from the yellow color that we're mixing on the periphery and the red color that we're mixing on the periphery. And then we have to put in another line, which line reflects the ratio of how much yellow and how much red, okay? Now where it gets a little tricky is the fact that in this diagram, the yellow color is actually represented on the red end of the spectrum. And if you think about that, the reason for it would be obvious. If we're going to mix a color that is almost 100% yellow and has just a smidgen of red, the color is going to be very slightly orange, but significantly shifted toward yellow. Okay? So in essence, putting the ratio of yellow closest to red is simply mathematically to reflect or to allow this mechanism to work, as I'll demonstrate for you here in a minute. So this portion down here represents the total proportion of yellow that is reflected here. And likewise then, the amount of red that is reflected is proportionally over here. So if we've got a mixture that is is more significantly yellow than it is red, then we shift this line over this direction. But this ratio of red to orange should accurately reflect what's happened. So in fact, if we had actually mixed 50-50, then this line would be exactly equal to this line. Okay? So the ratio that we've split here then gives us a very valuable piece of information, because where this line, the one that is radiating outward toward the color that we've actually achieved, where this line crosses this one, that is at this point, that defines the actual color that we produce. And it gives us two pieces of information. Not only does it tell us the color that we've got out here at the periphery, where the two lines cross actually tell us the saturation of the color. That is, how close to pure the color is that we end up with. Now, one of the obvious implications of that is that anytime you are mixing colors additively, you are by definition going to end up with a color which is less saturated than the ones that you mix. Okay? Because it doesn't matter where I put this second line over here, the line that is currently going to yellow, I can put it anywhere. But the line connecting them and the bisecting line is going to have a cross point that is somewhere within the circle, that is closer to the midpoint. Totally unsaturated colors would be right down here around the middle. Okay? There's no color at all right here. This is where black, gray, white would be represented. Are you with me? Now's a heck of a good time to ask questions if I'm leaving you, because I've got further to go yet, so make sure you understand what I'm saying. But in essence, this is a very simple, straightforward, plain geometry way to figure out what color you're going to end up with when you add color discs onto a stage floor or any white reflecting paper. Now, what I'm going to do is to change the nature of the demonstration here a little bit. I'm going to move this line over to the green-yellow dimension and then do exactly the same thing. Okay? So now, in essence, instead of having the orange hue and saturation, both of which we can detect from this diagram, what I'm going to do instead is now put the line over here at green. All right? And now we do the connecting line, and then we do the bisecting line. And in this case, what I've done is mix about equal parts of red and green. And so the net result now is a color that's going to be yellow. But look at where the cross point actually occurs here. It is much closer to the center point. Is that going to be a highly saturated yellow or a very pale yellow that has a lot of white or gray in it? It'll be very pale. The saturation level is very low in this case. Now, let's go even further. Now what I'm going to do is I'm going to move this point not to green, I'm going to move it exactly over to blue-green. And when we do that, the hue that we had, which was yellow, and the saturation, which is very weak, in fact is going to disappear. That is, when I make the line over here, notice what happens to saturation and hue. It totally disappears. This color, this blue-green, is what is called the complement of the red color. It is an exact complement of the red color. So that if we actually, on our stage lights, if we actually shined a red light and a blue-green combination, we would end up creating just white. So you don't actually need all four colors shining. If you've got two colors, in fact, that are exactly balanced, you can produce a situation where the one color wipes out the hue of the other, and you end up with some kind of shade of black, gray, or white in the combination. So in essence, if we mixed a yellow and a very slightly greenish blue, the net result would be white. If we mix red and a kind of a bluish green, the net result would be white. There are a number of different lessons that actually come out of this, among them lessons on how to dress. Because in essence, in order to decorate your body, where people don't kind of go, oh, what you need to do is to wear what are called complementary colors. So if you're going to wear only two colors, you do not want to wear red and yellow. What you want to do instead is to wear red and a bluish green. Or if you're going to wear blue, you wear yellow. If you're going to wear three colors, then instead of having a 180-degree line there in the middle, you're going to have a three-way split of 120 degrees each. So in that case, if you were going to wear three colors, you would wear perhaps a red, a kind of a yellowish green, and a deep bluish green, which would give you three colors. If you're going to mix in four, then you want to do red, yellow, blue-green, and intensely blue or indigo. Okay? So that you want the balance of the complementary colors in terms of something that's pleasant to look at are going to be a balanced representation on this chart that we're looking at here. Another practical advice for good living. Now, in this case, the saturation level is non-existent. That is, we're just right at we're on the black, gray, white scale. So there is no color to be saturated other than the black, gray, white. And there is no color present at all in this situation. Now, let's go to the eye and look at the receptor that has produced this effect. The eye has a number of fascinating aspects to it that we'll try, as many as we have time, of which I will try to talk to you about today. In essence, what we're going to look at, we're going to take a journey. We're going to follow a light ray through the eye and show you the kind of effects that occur. I'm not going to hit all of them. I'm going to stop on some of the more interesting psychological features here. One of the first things that is to be noted is that there are two humors in the eye. You'll see up on the top left of the screen is an area called the aqueous humor. That's in yellow on the diagram. The blue area further back in the eye is what's called the vitreous humor. Both of those are areas of the eye that are filled with fluids. And I'll come back and talk about the reason for that here a little bit later. But the first apparatus that is really of significant interest to us is at least speaking as a psychologist, is the iris, which is down on the lower left of the eye and in terms of the label. And the iris is basically the colored part of the eye. So in essence, when on your Texas driver's license, when they ask you what color, what they're really asking you is what color is the iris of your eye. The iris is the light control device on the eye. That is the single most important device on the eye for controlling how much light actually gets in. The brighter the light, the better your focus is. So in essence, when the light gets bright, in fact, what I'm going to do is to cut sideways through the eye and show you a head-on view. In other words, if we roll around to the front of this eyeball and look straight in, this is what we see if we look very carefully. In essence, the red part of the circle here diagrams the pupil itself. The pupil is the black center part of the iris, which is where the light is actually going in. If you'll look at the diagram here, however, what is diagrammed here are the two ways in which the muscle cells are oriented around your pupil. That is, the iris actually has muscle cells that are organized in two different ways. You are probably, from basic biology, already aware of the fact that muscle cells operate by constricting. That is, they shorten. So when you pull your arm up, it's these muscles that are the cells of which are constricting to pull the arm in. Okay? The iris works in exactly the same way. That is, when those cells that radiate outward around the center shorten, the effect is that it widens the iris. That's what happens when you go from a Texas summer afternoon sun into a movie theater. Okay? Those cells shorten, and the net effect is that it pulls the iris wide open. It lets in as much light as it possibly can. You don't have as much depth of focus, but you can let in a lot more light by a factor of 5, 6, 7, 8-fold relative to what you had out in the Texas sun coming in. On the other hand, if you walk out of the movie theater into the Texas sun, what hurts when you get that experience of ouch from your eyes, it is the ciliary muscles in the iris, which are being asked to constrict very rapidly. Because in essence, when you go from a darkened or semi-darkened movie theater out into a bright afternoon sun, your eyes are going to tell you about it. It doesn't physically hurt them, but they do grumble when they have to shorten that rapidly and that far. Those are the circular cells that are oriented right around. I've got them in pink on the set if your color is well adjusted. The cells that are in the dashed lines right around the iris, those constrict, and the net effect is to close down the iris and make it very, very small. So your assignment tonight, should you choose to accept it, is that I want you to gaze deeply, not into, but at the eyes of your beloved tonight, and see if you can actually see these muscle cells. You have to look closely, but you should be able to detect them if you look very, very closely. And you'll see that the ones that are right around the pupil are oriented around the pupil. The ones that are further out are radiating outward. And if you watch the eye, when you flash light into your beloved's eye, you will see the cells constrict or decrease the size of the cross-section of the pupil. Now, let's go back and look at the eye again and continue our journey. The next thing that we get to is the lens. That's the clear white substance right in the middle of the almost dead center in the screen there. The lens is an amazing object. It takes about 2 pages of single-spaced typewritten print to describe all of the things that actually represent what the lens is. But in essence, what it boils down to is a clear, elastic human substance. It is clear, at least for those of you who are age 25 or younger, and it is elastic. By the time you reach my age, a lot of it has solidified in ways that we'll talk about here in a couple of minutes. But in essence, the lens is the primary thing that is responsible for focusing the lens, the rays that are coming into your eye. Now, if you're short-sighted or far-sighted, what's happening is that the image at the back is falling either too close to the lens or too far back, that is beyond the retinal surface, which we'll get to here in a minute. But in essence, if you are in fact young and you have 20/20 vision, then in fact the image is in focus right on the retina. The rays are bent to exactly come into focus on the retina itself. But let me suggest that you try an experiment with yourself. What I'm going to ask you to do is to look at my nose, and hopefully you're sitting some distance back from the TV set when you do this right now. Get as far back from the set as you can in order to do this. What I'm going to ask you to do is to close one of your eyes and look over your index finger at my nose. Okay? And what I want you to do is to put the pointer that we're going to use right up under the line of sight so that you're looking just over your index finger at my eye using one of your eyes, only one open. By the way, whichever eye you opened is likely your preferred side. See if it correlates with your handedness. But in any case now, what I want you to do is to shift your focus back and forth using only that one eye. focus first on my nose that is on the TV set, and then focus on your finger. So I want you to get your finger as close to your eye as you can and still focus on it using just your lens. And then I want you to shift your focus back and forth from my nose to your finger, back to my nose to your finger. Shift it several times and then answer from me a question. Which direction can you shift faster? Can you shift faster from your finger to my nose or from my nose to your finger? And the question is, now let me make sure I ask this correctly. How many of you can shift more rapidly from my nose to your finger? How many of you can shift faster from my nose to your finger? And how many of you can shift more rapidly from your finger to my nose? Which should be the correct answer. Okay? And the reason is that the lens is one of the very few elements in the body, in fact, one of only two I know of, where a physical action is not accorded or is not caused by muscle contraction both ways. Okay? In essence, if you look back at the diagram of the eye again, the ciliary muscles, I'm sorry, I mislabeled that earlier. The muscles that are in the eye have a separate name, and I meant to go look that up this morning and I forgot to. I will get that to you in the next lecture. The ciliary muscles are actually the muscles which, when they constrict, flatten the lens. Okay? So in essence, when I'm asking you to shift your gaze from my nose to your finger and back, what I'm doing alternately is having you tell your eye, tighten the ciliary muscle to thin the lens when the image is far away, and relax the ciliary muscles so that the elasticity of the lens will fatten it out when the image is close and the light rays have to be severely bent to reach your eye. I'm not diagramming that well. If the object is close to the lens has to fatten out a lot because the light rays that are coming in have to be sharply bent in order to focus them at the retina. Okay? The point is that you and I can use muscle strength to thin the lens much more rapidly than we can rely on elasticity. And that effect gets worse. That is, the difference between those two adjustments gets worse the older you get. By the time you reach my age, 61, the lens is basically not working any longer. It has solidified over years, and that's the reason you will see people who at age 40 suddenly grumble that they've reached the end of their arms. And what they're talking about is that when they're trying to read something without glasses, they have to hold the newspaper this far out, and they can't go any further without the help of a husband or wife, and therefore it's easier to go get bifocals. What's happening now is when you have bifocals, is that you've got one focusing power for when you're in here, and you've got a second one for when you're looking at the horizon and related phenomena. Okay? So in essence, what we're dealing with there is the elastic function of the lens and the ability of the lens to differentially achieve focusing for different kinds of objects in terms of the nearness or the farness. The next object, as we look at the eye again, is the vitreous humor. Have you ever had the experience of looking out at a clear blue sky like we do get here in Texas, and noticing that when you're staring right up at the sky, so you've got a large field of very constant blue, there's something floating kind of out in right field, and you kind of dart your eyes to look at it and it's still in right field, and you dart your eyes to look at it and it's still in right field, and when you get all the way back around to where you started, that object is still over there. You ever had that experience? What you're looking at there is what's called visual dust. The reason you can't look at it is because it's within the eyeball, that is, it's in the vitreous humor. There are 3 points relative to vision, all of which are fixed, which prevent you from being able to look directly at it. The point of entry of light into the eye through the pupil, through the lens, is fixed. The place where the visual dust is located is fixed, and the sensing point on the retina at the back is fixed. And the result is all 3 of those turn as a unit. And so it doesn't matter where you look, up, down, left, right, or backwards, you cannot see visual dust directly. It will float there and eventually be absorbed. What it represents, it isn't like if you turn yourself upside down, you're going to be like this Santa snowball thing where stuff is filtering down through your eyes. What's represented there typically are things like rods or cones. Some of the sensing surfaces have sloughed off and are simply floating in the eye. They will eventually be absorbed and removed by the circulatory system, the blood system. But sometimes it may take a year or 2 or 3, depending on the size of the object, before that total dilution effect actually takes place. But that visual dust that you see is actually in the vitreous humor. Now, at the back of the vitreous humor, excuse me, we have three surfaces that I'm going to talk about, and then I'm going to talk about one in detail. The first surface that you reach is the retina. The retina is the sensing surface for the eye itself, for the visual image. I'll come back and talk about that in a minute. Immediately behind the retina is what's called the choroid layer. The choroid layer is a black layer immediately behind the sensing surface. Why would that black layer be there? Why would we need to have the choroid layer there in the eye? There are actually two reasons for it. Why would you need it? Ugh. I'm paid, so I can outweight you. We're wasting hundreds of thousands of dollars of television time here.
Keep your eye from falling out.
Keep your eye from falling out. Well, no, the two layers out is what accomplishes that. No, but you think about it. Let's go the exact extreme. Let's suppose instead of a black layer, you had a mirrored surface there. What's going to happen to that light ray when it comes in and stimulates the rod or cone, the receptor surface? Yeah, it's going to bounce back out. It's going to stimulate that cell again, and then it's going to hit somewhere else and stimulate it again, and again, and again. You think LSD gives you a trip, you ought to try a mirrored eyeball sometime. Okay? So in essence, the first reason and the primary reason for the choroid layer is to absorb the light as soon as it has stimulated the rod or cone that it's hit. Okay? The second reason, which is a little more subtle, is the fact that you may remember the old saying from the Revolutionary War, don't shoot till you see the whites of their eyes. Well, the whites of the eyes for you and I, when we turn to the side, represent an area where light could actually leak in. And so in order to prevent light from coming in from the outside, other than through the lens, that's a second purpose of the choroid layer, is to absorb, or in that case, to block light from coming in from the outside. So that's the choroid layer. The last layer is the sclera, and that's the one that helps the eye retain its shape. You think about it a minute, you do want that sclera to be absolutely rigid, because otherwise what happens on the middle of a hot Saturday night date, your blood pressure goes up to 160, your heartbeat per minute is 226 and climbing, and your eye is now, your visual system is now flashing every time. When the heart beats, if the eye pulses, the result is your vision absolutely deteriorates. I will leave it to you to imagine all the things that might happen as a result of that, but the point is that the sclera is wrapped very tightly around the aqueous humor and the vitreous humor and provides the solidity for the shape of the eyeball itself. Now let's go back and look at that sensing surface for just a minute, okay? You will see in the bottom right corner of the eye at about 4:30 o'clock on the diagram, 4 o'clock there, is where the optic nerve enters the eye. Or the other way to think of it is that's where the optical cells come together and leave the eye, which is what's actually happening. But in essence, when those cells come in to the eye, they form a kind of an umbrella-like arrangement. That is, the cells make a U-turn so that the rods and cones are actually pointing away from the source of light itself. Okay? That's the reason that there are two things that result from this kind of an effect. First of all, there's a blind spot right where the optic nerve enters or exits the eye. I guess exits the eye is a better way to think of it. Because these sensing cells, the rods and cones, synapse to what are called bipolar cells, which synapse to ganglion cells, which are what form the optic nerve. And because of this arrangement, right where the cells reverse, where the optic nerve leaves the eye, there are no sensors right at that point. That gives you a blind spot, which I'll come back to in just a second. The demonstration before that I wanted to do is to notice that basically when we, where was I going? I hate it when I get 2 steps ahead of myself and then lose track of what I was going to say. The point is that you can actually take a big sheet of cardboard, this is what I want to say, take a huge sheet of cardboard that blocks out most of the light, use a pinpoint light source other than the sun, and put the very cleanest, smallest hole that you can through that cardboard, and then look through the hole with a single eye. And if you move the cardboard, what you're doing is causing just a pinpoint of light to move back and forth on the surface of your eye. You will actually sense that light is flickering. And the reason it's flickering is because what happens is when you've got that very, very narrowly constricted light beam, what it's actually doing is hitting the nerves and the various cells, blood vessels particularly, on the surface of the eye. And the blood vessels particularly are casting shadows on the sensing surface below. So when you move that light and it seems to flicker, the reason it's flickering is it's off the nerve, it hits a nerve, it's off the blood vessel, it's off the blood vessel, hits the blood vessel, it's off the blood vessel, and so forth. Anytime that light beam goes across a blood vessel, it blocks out and the eye gives you no visual experience. Let's go even one step further and look at the, I'm not sure whether I want to do this quite yet or not. No, hang on a second. We'll come back and look at the blind spot in a little bit. When we look at the shape of the eye itself, the other point to notice then is the focusing, as I've already talked about at least a little bit. That is what's called accommodation. That is what the ciliary lens and or muscle, I should say, which flattens the lens accomplishes. It does what is called accommodate to the incoming light. That's the focusing that occurs. Nearsightedness or myopia occurs if the eyeball is too long, so to speak. That is, if the image is in focus in front of your eyeball, in front of your retina, that is between the retina and the lens, then you are nearsighted or myopic. If, on the other hand, you're farsighted, then what's happened is the image is focused behind the retina. Now, the retinal surface itself is actually 3 layers deep, as I've already indicated. And now let's take a look at the blind spot. I'm going to diagram on the screen here, but I want you to look at an X. There is in the Simple Psych book at the top of the next page a diagram for what I want you to do, and that is an X and a circle. All right. The question is, if you close your left eye, look at the cross with your right eye, and move the book back and forth, that is toward and away from your eyes. And I should not say that. Yes, toward and away from your eyes. Can you see the circle? Okay? So what you're going to do is to close your left eye, look with your right eye at the cross, and then pull the book towards you and away from you slowly. At roughly a comfortable reading distance, do it slowly so you've got time to react to it, but at roughly a comfortable reading distance, what happens to the circle? It disappears. Miracle of miracles. This is the first of several demonstrations that I promised you where the way you see the world is not the way the world is actually operating. This is a case where your visual system is actually lying to you. Okay? What I'm saying is, when I close my right eye and stare at the camera, there is for my right eye an area over about here where I cannot see what's actually going on. Now, where you're sitting right now, given that you're in an environment that you're comfortable with, if you shut one eye, you are not aware of that blind spot because you have scanned your eyes so many times across the environment that you know what's there. And your brain actually fills in that information for you. But you will notice that every now and then you will read an article in the newspaper where some farmer or rancher out in West Texas has come up to the county road or the county highway, the state highway, and then pulled right out in front of an oncoming 18-wheeler and killed himself. And what's probably happened there is that he looked once and looked the other way once and pulled out. And what happened was that the mirror or the corner post of the car or something blocked the image that was going to fall on the left eye where the blind spot is not, and it fell on the blind spot of the right eye, so he drove out in front of a truck or a vehicle that he literally never saw. Now, suggestion for happy living, anytime you come to a T intersection and are pulling out into traffic, always look twice both ways. The reason being that if the object is coming fast enough to hit you, it is also coming fast enough to move off your blind spot. The blind spot for the right eye is toward the nasal side, and the left eye is also toward the nasal side, so they're non-overlapping. So when you've got both eyes open, the blind spots are covered by the other eye. But in fact, they can cause you some difficulties in processing information under certain kinds of situations. We'll show you some other examples of where your eye is lying to you here shortly. Now, let's look at a little bit about how the rods and cones actually function here. The cones are actually distributed only in the center of the eye in an area called the fovea. I meant to point that out on the diagram earlier. It is in the Simple Psych book. If I ask you to look at something, as I did earlier, what I'm telling you to do is cause the image to fall right on the fovea, which is dead center in your eye. And that area is occupied only by what are called cones. The cones are the color receptors in the eye. The rods are black-white receptors. Okay? The net result is that there are a couple of things going on as you go into a movie theater. But before I do that, I want to demonstrate one thing, and I'd like to ask the camera people to come back to me and follow me out, because I want to do a demonstration here. I need to have somebody who's got good 20/20 color vision do a demonstration for me. Who's got 20/20 color vision? Okay, if you can come up for a minute, what I'm going to ask you to do is to sit on the chair here and pick a spot out on the far wall that is pretty much straight ahead. And then what I'm going to do is start way around behind you. Can you see? What I'm going to ask you to do is look that way, and I'm going to be holding an object in my hand, and I'm going to want you to tell me, first of all, when you can first see it. If I'm back here and you pick an object, say your own reflection or something over straight ahead there, and if you look there, can you see something in my hand now? Okay, then I will start there. Shut your eyes for just a second so I can get the object I'm going to use. Okay, I'm holding a pencil-like object in my hand. I want you to tell me when you're first aware that you can see that object. I'm moving it vertically just about at eye level. Tell me when you're first aware that you can see the object. Okay, I'm just about even with the back of his head. Okay? Don't look, it's going to be very tempting. All these people are going to tell me if you move your eyes, your course grade drops 2-letter grades. Okay, so they have some vested interest here. What color do you think the object is? Black or gray, okay. Now I come around here, and again, keep your eyes straight. I will get directly ahead of you eventually. What color do you think it is? Red. What confidence between 1 and 10? 1 lowest meaning low confidence, high meaning high confidence. Okay, how about now? 5. You still going with red? How about now? A 3, but still going with red? You want to switch to anything else? 1 is at least confident. Okay, all right, then maybe I shouldn't have switched scales on you, but you've gone from, you're gaining in confidence. Okay. A 10. Okay, we'll give it to you. It is a red. Okay, thank you. If you will try that with other people, what you will find is normally, and you could hear it in his numbers, normally what happens is the range at which they can actually detect red is only about 10 degrees out of dead center. And we didn't, that was the only color he guessed, but I've often had people, and in fact usually have people, who will guess blue or a dark color of some sort. And in fact, the point is that the rods do not see red. They simply, well, they see the object, but they don't interpret red. They report it simply as black, which is the reason that naval aviators, or any aviator who needs to fly at night, will walk around with red goggles on, because in essence what it does is to trick the rods into dark adapting. So if we can go back to look at the diagram, in essence what you see here is the color sensitivity, the sensitivity to light of the rods and the cones. And in essence, you can see that the rods, first of all, are markedly more sensitive to light, but also notice that the area of greatest light concentration or greatest sensitivity is different for the two objects. That is, cones are maximally sensitive to kind of a greenish yellow. The rods, on the other hand, are sensitive to a green that is much further down toward the blue end of the range, or a bluish green. The net result is that you exhibit at sunset what is called the Purkinje Shift. That is, you're going from cone-based vision, i.e. day vision, to rod-based vision, which is night vision. And that increases your sensitivity to greenish-blue colors, and the net result is, that's the reason that when you see a painting of a sunset, which is an artist's representation, it is toward the purple or blue end of the spectrum. But if you paint a sunrise, then you're more likely to use yellows and oranges and reds, because now you're coming from rod vision back to cone vision, which is more sensitive at the yellow-red end of the spectrum. That is what's called the Purkinje Shift. The other diagram that I'll show you here, and we'll come back and talk about next time, is what happens in terms of dark adaptation. That is, when you go into a movie theater, your rods will adapt, adjust to dark adaptation, but it takes them about 10 minutes to kick in. The cones kick in fairly rapidly, but only adjust about 1 log step. By 30 minutes, you're then fully dark adapted, and we'll come back and look at the combined effect of the Purkinje shift and dark adaptation at the beginning of the next lecture.